In this lecture, we continue our discussion on cache memory organization. We start by discussing the effect of line size on cache miss rates. So, larger the size of cache lines, higher becomes the spatial locality and therefore, lower becomes the miss rates. We discussed about spatial locality in the last lecture. What is spatial locality? The words that have been discussed, that have been accessed recently, the words nearby them are highly probable to be accessed in the near future. So, when cache lines becomes larger, so there is a higher probability that words that are nearby will be accessed. So, we get more words which are nearby and therefore, cache miss rates reduce. However, when the cache lines grow from say 8 kb to 16 kb to 32 kb and so on, when it grows after a certain time, miss rates eventually grow. Instead of reducing, miss rates grow when the line size becomes a significant fraction of the cache size. Why does this happen? Because the number of cache lines reduce when the size of one cache line increases, given a fixed size of cache, the number of lines in the cache reduce. So, we have lower number of lines and therefore, higher competition among memory blocks for these lines. Therefore, cache performance reduce, and therefore, a line is bumped out of cache before many of its words are accessed. So, we wanted to increase cache line size because we wanted to get more words which are nearby words that have been accessed recently. However, before those words which have now come within the vicinity due to a larger cache size can actually be accessed, they are bumped out. Why? Because the number of lines in cache are now much lower. So, therefore, effectively spatial locality among words of the line reduces. Now, larger lines also means a higher miss penalty. And what is the definition of a miss penalty? It is the time required to fetch a line from the next lower level of memory. Let us say main memory and cache, for example, here it will be main memory. We can have multiple levels of cache as well. Therefore, in general, I have written it as lower level of memory in the hierarchy and load it into cache. So, miss penalty is the time required to fetch a line from the next lower level of memory hierarchy and load it into cache. Now, this time to fetch this miss penalty has two parts to it. One, the latency to fetch the first word from the memory into the cache, and the transfer time for the rest of the block from lower level memory to the cache. Now, larger cache line size means higher transfer time, because you have to transfer more data from the memory into cache. So, improvement in miss rate also reduces with large size caches. Now, along with this higher transfer time, improvement in miss rates also reduces, as we said that with significantly large size caches, when they become comparable to the size of the cache line size, then the miss rates also increase, that is, improvement in miss rate reduces. Thus, cache performance reduces when line sizes are too large. However, this higher transfer time, if we can reduce, so one aspect of due to which the performance reduces can be checked if the transfer time can be reduced. So, line size can be increased to some extent with better block transfer techniques, and here we will discuss two block transfer techniques. One is early restart, that is, resume execution as soon as requested word is returned instead of waiting for the entire block. So, in general what happens is that when we have requested a word from cache and that word is not in cache, we have a cache miss, and the entire block is first fetched from main memory or lower level of memory into cache, and then execution starts. Early restart says that instead of doing this, resume execution as soon as the requested word is returned instead of waiting for the entire block. It works best for instruction accesses because they are largely sequential. So, if the transfer rate is 1 word per clock cycle, the memory system may be able to deliver new instruction words to the processor just in time. So, what does it say? If the transfer rate from the main memory into cache is about 1 word per cycle, per clock cycle, then what happens? The processor gets a new instruction every clock cycle. So, once we have got the word that we need, so that is the what is the word that we needed? The instruction that we wanted to execute in case of instruction access. Now, the next instruction is the next word in cache in that block. So, we have not waited to get the next word. However, once the processor executes the current instruction, the next instruction is available because we have said that it takes about one cycle to load 1 word from the memory into cache. So, therefore, we get the instruction words just in time as they are required. So, they become this early restart mechanism could be very effective in case of instruction accesses. However, they are less effective for data caches because data word requests are typically less predictable. Why? Because we require sequential instructions one after the other. Data accesses may not be such sequential. Request for a data word from a different cache line before completion of transfer is high. So, therefore, in case of early restart, what have we said that? We said that we will get the data word in case of data access, we will get the data word, we will not wait for the entire block to be transferred from main memory into cache, and instead whenever we get the required data word due to which the miss has occurred, we will immediately start execution. Now, if we do this for data word, there is a high probability that we will request an word from a different cache line before completion of transfer, and this will what will happen if this happens? What is the problem? The problem is that there is one transfer which is currently going on from the memory into cache. Now, for the second transfer to start, the first transfer has to complete. So, there will be a lot of memory stalls. So, processor stalls if data cache is inaccessible due to an ongoing transfer. This is the problem. The next mechanism to improve transfer rates is the critical word first. This is a more advanced technique. Early restart said that we will start getting words of the block from the start of the block. However, once we get the data word that due to which caused the miss, we will immediately start execution. Critical word first says that don't start your transfer from the start of the block. You start the transfer from the data which caused the miss. So, you first get the data which caused the miss from the memory and start execution, and then transfer the rest of the block. So, transfer requested data first, then transfer rest of the block starting from the address after the requested word and wrapping around to the beginning of the block. Before proceeding further, we will first quickly discuss about how cache misses are typically handled. So, we will talk about how to handle instruction cache misses. A very similar technique is used for handling data cache misses. So, if instruction access results in a miss, so what has happened? I wanted an instruction, I floated the PC with an address. Handling instruction misses. So, next we will talk about how to handle cache misses. We will specifically talk about how to handle instruction misses. A very similar technique will be used for handling data misses. So, when we do not find the instruction, the next instruction that is to be executed by the processor in cache, and instruction miss results, and then the instruction register content becomes invalid. So, what is the address of the instruction then that has to be fetched from memory, because it is not in cache? It is the content of PC minus 4, because in the first cycle of in the first cycle of execution, PC is incremented. So, the value of PC is 4 plus the instruction for a 32-bit computer is 4 plus the instruction that I want from memory. So, the address of the instruction actually is content of PC minus 4. So, what are the steps for getting this instruction from the main memory? The value of PC minus 4 is first sent to the memory. Then we instruct main memory to read and wait pipeline stall. So, we instruct main memory to read, and then the processor waits, that means pipeline stalls happen. So, what is the meaning of a pipeline stall? Temporarily all the data and all the contents are frozen, okay, and the processor does nothing, it just waits until the data or the instruction is obtained. So, instruction the processor instructs the main memory to read, and then it itself waits for the main memory to complete transfer. Then during the transfer, we write into the cache entry. What do? We put data from memory into the data portion of the entry, and the remaining tag field is then populated into the tag entry in the tag part of the entry. So, into the tag part of the entry, and we turn the valid bit on. So, once both the tag and the data has been put into cache, we get we put the valid bit on and say that the content of cache is now valid. Then we restart instruction execution at the first step of the pipeline. This will refetch the instruction, and this time it will find it in cache. So, this is how it will handle a miss. Handling writes is a bit more complicated than this. So, how do we specifically handle write? Before starting as to how to handle writes, we first talk about what is inconsistent, what is the meaning of inconsistency between cache and memory. Suppose on a store instruction, we wrote the data only into the data cache without changing memory. Thus, memory and cache will have different values after the write, and this is what we term as inconsistency. So, during a store, we have written the data into cache, but this corresponding data we have not, this updated data which is there in cache has not been populated into the main memory or the lower level memory. So, therefore, the lower level memory block and the cache line data corresponding to this word becomes inconsistent. Now, we have two types of write policies. The first is write through. In the write through, it is a scheme that keeps cache and memory consistent by always writing data to both memory and cache. So, the inconsistency that we were talking about before does not happen here, because whenever we write into cache, we also write into memory. So, on a write miss, what happens? We fetch the block from memory into cache first. We overwrite the word that caused the miss into the cache line, and we then also write the word to main memory using the full address. So, now every write also affects a memory write as well. Every write into the cache is also a write into the memory. Why? Because we are keeping everything consistent. If the write is a miss, it is not there in cache, then the cache block is first fetched from memory into cache, then the word which caused the miss is overwritten into that line, and then that word is also written back into the corresponding memory block. This policy has significant overheads and therefore results in inefficient performance. Why is that so? Every write causes data to be written into main memory. So, memory writes, as we know, takes a long time, at least say 100 clock cycles. So, if the CPI without cache misses was 1.0, and if 10% of the instructions are stores, then the effective CPI becomes 1 plus 100 into 10%, which is 11. So, therefore, the performance reduction happens by a factor of 10. So, here 1 is the CPI without any write misses, okay, without any writes in it, because all writes will go into memory. So, without writes the CPI is 1. For every write I incur 100 cycles, because I go into memory and write the word also into memory. If I have 10% stored instructions, each of these instructions will cost me 100 cycles, and therefore, if for 10% instructions with 10% stored instructions, the effective CPI becomes 11 and the performance degrades by a factor of 10. So, one solution to circumvent this problem is to use a write buffer. So, what is a write buffer? A write buffer is basically a queue that holds the data while it is waiting to be written into memory. So, execution can continue after writing the data into the cache and write buffer. So, what happens here? We are not writing every write into memory and then proceeding again. Once we have written into the write buffer, we proceed with the execution and do not wait for that word being written into memory. Okay. So, after completing the write to memory, the write buffer entry will be freed. However, memory stalls will still happen, meaning that after a write, so during a write what happens? I am writing it into cache and also into the write buffer, and once the write buffer completes the write into the memory, that entry from the write buffer is removed. However, if there are too many writes in a burst from the memory, what happens? The write buffer gets full, because write buffers are typically of the size of 2 to 4 words. In any case, if the rate at which the processor writes into the cache is higher than the rate at which the transfer can be made into memory, whatever the size of the write buffer, we will still have a stall of the processor, because the write buffer will be full. However, typically that does not happen. Writes are on an average scattered, and therefore, it has been seen that write buffer sizes of about 2 to 4 words seem to be sufficient in the typical case. The other policy, so we talked about the write through policy, in which whenever I write both into the cache and the memory, or as a slight deviation we write into the cache as well as the write buffer. Write back works differently. It handles writes by updating values only to the line in cache and then writing the modified line to the memory that is lower in the hierarchy, in the main memory, or maybe maybe a lower level of cache when the line is replaced. So, on a write we only write into the first level cache, we do not bother about lower level memories at all. When this cache has to be replaced, this cache line when it has to be replaced, I see that the data in cache has been modified and therefore, is inconsistent with the memory. At that time I write back whatever is there in the cache line into the memory first and then replace that line. We do not replace before we have transferred a modified line in cache into the memory. Now, write back caches, as we understand, can improve cache performance. Why is that so? Because if I have, say, repeated writes into the same block, it can be coalesced together. If the same word is written again and again, it can be coalesced together. Okay. So, we and for many writes, we finally transferred it once together. So, this is why write back is typically better than write through caches. However, implementation of write back caches are more difficult, as we will see. So, for write through caches, we require only one valid bit. The cache line can simply be discarded during replacement. So, why is that so? In a write through cache, we are ascertain that the cache and the memory is always consistent. So, when we need to replace a cache line with another block of memory, then we just need to discard this cache line, because whatever is there in the cache is that up to date information is also there in the memory. For write back caches, however, we require two bits, one a valid bit and also another a dirty bit. So, the valid bit just tells that the word in memory is valid, is correct. The dirty bit says that the cache line, the dirty bit says that whether the data after it has been brought from memory has been modified or not. So, if a word has been modified after it has been brought from memory, then this dirty bit will be 1. This is required for write back caches, because I am not writing back every time I am writing to the cache. So, I am writing to the cache and I am not updating that to the memory, but I am setting the dirty bit on. So, it requires both valid and dirty bit. Cache line must be written to lower level memory before replacement if the dirty bit is on. For write through caches, read misses cannot result in writes. Okay. Now, when I have a read miss, what is the problem? I have a read miss in cache, that means somebody else, so some other cache line is now being held in the cache. So, whatever I want, the block of memory I want is not in the cache, the cache line is filled with some other memory block. So, therefore, I need to replace this line. So, when I have a write through cache, I just discard this line from cache, everything is consistent, and I write whichever and I just transfer whichever block is necessary from memory into cache. For write back caches, this is not possible, as we have seen. Now, for write through caches, we can either have write allocate or no write allocate policy. So, consider write misses in a write through cache. So, in a write allocate policy, so we are considering write misses in a write through cache. So, in a write allocate policy, the block is fetched from memory and then the appropriate block is overwritten. In a no write allocate policy, we do not allocate new cache line. We directly update the appropriate portion of the block in memory. So, what has happened here? In a write through cache, we do not have a write hit. That means, the data that I want to write into cache, that data is not present in cache. That particular cache line holds somebody else, some other memory block. So, therefore, I need to replace. So, in an allocate policy, I first replace from memory into the cache line, right, and then I overwrite. So, the block is fetched from memory and then the appropriate block, appropriate data is overwritten into both the cache and the memory block. In a no write allocate policy, I do not bring in the new cache line. I directly write the word that is to be written directly into the memory. So, I do not bring from memory the cache line. So, when is this advantageous? A typical use case is that, say when the OS initializes an entire page of memory. So, it has an entire page of memory, it will fill it with zeros. So, a full block of memory is going to be filled with zeros. If we bring that whole memory block into cache, I have to write each word into cache, and then I have to also write each word into the memory, and this is an overhead. Instead of that, in a no write allocate policy, I do not bring the cache line at all, and what do I do is I directly write those words directly into memory, not bringing the memory block into cache. So, this helps save overheads. Efficiently implementing stores in write back cache is more difficult. For a write through cache, it is much simpler. On a write miss, what will happen? I will try to write my data into cache. If that cache line is not the one into which I should be writing, the memory block is different, then at most what will happen? I will write in on a wrong word, and then I will see that this is a write miss, and I will replace the cache and maybe write again. This is not a problem, because the memory is always consistent with the cache. In a write back cache, as we said, the cache is not always consistent with the memory. So, if I write without seeing anything, whether the data in the cache is modified, I have the problem of or the risk, I have the risk of overwriting some data which has not been actually written into memory. So, I have the risk that this write, so I have not checked whether the data in the cache has been modified or not. So, this word, the dirty bit for the word is on or not. If the dirty bit for the word is on, this means that this word has not been written into memory. Okay. If the dirty bit for the word is on, this word has not been written into memory. Now, if I do not check that and write my data into a write back cache, I have the risk of overwriting inconsistent data. Okay. So, therefore, in write back caches, I first need to check whether this is a cache miss or whether this is a write miss or not. If this is a write miss, that means the cache line that I am writing into is not the one corresponding to the memory block in which I should write, then I should first make the memory and cache consistent, then replace the cache line and then write it into the proper cache line. Okay. So, therefore, implementing stores efficiently in a write back cache is more difficult compared to a write through cache. Now, we will take a few examples for measuring cache performance. We will do some small sums to evaluate the performance of cache. To start with that, we will talk about the components of CPU time. We will first do a simplifying assumption saying that CPU time has just two components. One is the program execution time, and this we will assume to include cache hit time, as we will say that cache hit time is part of the processor execution of instructions. We will not take hit time separately, and along with that there will be memory stall time, memory stall cycles, mainly due to cache misses. So, the CPU time required to execute a program will be composed of two components. One is the program execution cycles, that will include cache hit time, and memory stall cycles, this will include cache misses. Now, with simplifying assumptions, we will say that memory stall time is equal to memory accesses per program, number of memory accesses per program, into miss rate into miss penalty. So, miss rate is how many miss rate or miss ratio. So, how many out of the total number of memory accesses, what percentage results in misses in the cache. So, why we are saying that this is a simplifying assumption? See that we said that reads are typically lower in cost with respect to writes, okay. But we have assumed here that for all memory accesses miss penalty is same. So, this is the simplifying assumption that we have done, and we can also, in other words, we can also say memory stall cycles as number of instructions per program into number of misses per instruction into miss penalty. So, this is the other way of saying how much is the memory stall cycle, and the total CPU time of the program will be program execution cycles per memory stall cycle. Now, if we consider hit time, if we take hit time into consideration, then the average memory access time will be given by hit time plus miss rate into miss penalty. So, we will take 4 examples, the first of which is as follows. Assume the miss rate of an instruction cache is 2% and the miss rate of the data cache is 4%. So, miss rate of the instruction cache is 2% and miss rate of the on the data cache is 4%. Here therefore, we are assuming that we have a split cache and not an unified cache. We have separate instruction caches and separate instruction cache and separate data cache. If a processor has a CPI of 2 without any memory stalls, right. So, for a perfect the perfect CPI without stalls, memory stalls, and the processor executes absolutely smoothly, then the CPI is 2. So, the cycles per instruction is 2. I require 2 cycles to execute 1 instruction without any memory stalls, and the miss penalty is 100 cycles for all misses. Determine how much faster a processor would run with a perfect cache that never missed. So, assume the frequency of all loads and stores is 36%. So, we have assumed here that loads and stores, that is reads and writes, have the same penalty, and the frequency of loads and stores is 36% out of the total number of instructions executed. So, we proceed by saying that let I be the total number of instructions in a program. Okay. So, the number of memory stall cycles due to instruction access misses. So, I am trying to access instruction, I will miss how many times? We said that 2% the cache is 2%. So, miss rate of an instruction cache is 2%. So, 2% of all instructions result in misses. So, I into 2%, and for each such miss, the miss penalty is 100 cycles. Okay. So, so what is the total number of memory stall cycles due to instruction access misses? I into 2% into 100 equals to 2.0 into I. Number of memory stall cycles due to data access misses. We said that 36% are data accesses out of the total number of instructions. So, I is the total number of instructions, out of which 36% are data accesses. Out of these data accesses, 4% are misses, and all such misses take 100 cycles. So, the memory stall cycles due to data access misses becomes 1.44 into I. So, the total number of memory stalls composing both instruction access misses and data access misses become 2 into I plus 1.44 into I equals to 3.44 into I. Thus, the total number of cycles per instruction including memory stalls become 2 plus 3.44 equals to 5.44. So, for the perfect CPU when there are no memory stalls, perfect processing, we have 2 and we have additional 3.44 per instruction, 3.44 we have memory stalls. So, the total number of cycles per instruction become 2 plus 3.44 equals to 5.44. So, therefore, CPU time with stalls divided by CPU time with perfect cache is 5.44 by 2 equals to 2.72. This is what was required. So, the question was how much faster a processor would run with a perfect cache that never missed. So, how much faster would it run? It would run 2.72 times faster than a processor which misses at this rate as shown in this example. Example 2, the same instruction we will now see what happens when we make the CPU faster. We will see that the effect of memory stalls become more pronounced. So, we have now made the processor faster and the CPI has been reduced from 1 to 2. So, reduced to 1 from 2. So, therefore, now I take only one cycle per instructions. Previously, I took 2 cycles per instruction. So, the total number of cycles per instruction including memory stalls will now become 1 plus 3.44 equals to 4.44. Okay. So, there is a mistake in this slide, this 5.44 will be 4.44 in the first line. The system with perfect cache will therefore be 4.44 by 1 equals to 4.44 times faster. Okay. Now, so previously the system with perfect cache was 2.72 times faster. Now, the system with perfect cache will be 4.44 times faster. So, therefore, the effect of memory stalls have become more so pronounced in this case. The percentage of time spent on memory stalls will rise from 63%, that is 3.44 by 5.44. So, the percentage of time spent on memory stalls. So, 3.44 out of the total of 5.44 I wait for memory, I wait on memory stalls, right. So, 63% of the time I wait on memory stalls. Now, when the CPI becomes faster, when the machine becomes faster, the CPI reduces, then the effect of memory stall becomes more pronounced. So, now this ratio increases to 3.44 divided by 4.44 and which is 73% of the total time. So, now in the faster processor I will wait 73% time on memory stalls. Now, we come to the third example. What we have to do is the following: find the average memory access time of a processor, with 1 nanosecond clock cycle time, a miss penalty of 20 cycles, a miss rate of 0.05 misses per instruction and a cache access time including hit detection of 1 clock cycle. So, we assume that read and write miss penalties are same again in this case. So, as we said before, the average memory access time, which we also call the MAT in short, is hit time plus miss rate into miss penalty. So, we said that the hit time is 1 clock cycle. My clock cycle length is 1 nanosecond and my hit time is 1 clock cycle. Cache access time including hit detection is 1 clock cycle and my miss rate is 0.05. So, out of 100 instructions, only 5 instructions miss, okay? And each such miss causes a penalty of 20 cycles. So, the total miss penalty becomes 2 cycles, which is 2 nanoseconds. So, the average memory access time AMAT becomes 2 cycles, or that means 2 nanoseconds, because 1 cycle is 1 nanosecond in length. The last example we will take is the following. The memory access time is 1 nanosecond for a read operation with a hit in the cache. So, for a read operation, when I have a hit in the cache, I take 1 nanosecond. memory access time. Memory access time is 5 nanoseconds for a read operation with a miss in the cache. Memory access time is 2 nanoseconds for a write operation with a hit in the cache, and memory access time is 10 nanoseconds for a write operation with a miss in the cache. Execution of a sequence of instructions involves 100 instruction fetch cycles, 60 memory operand read operations and 40 memory operand write operations. So, instruction fetch cycles are how many? 100, memory operand read operations are 60 and memory operand write operations are 40. The cache hit ratio is 0.9. So, that means 90% of the times I have a cache hit, 10% of the times I have a cache miss, and in those times I have to go into the memory. So, now I have to find out the average memory access time in nanoseconds in executing this sequence of instructions. So, the time taken for 100 instruction fetch cycles. So, each instruction fetch cycle is a read, right. So, for 100 instruction fetch cycles I have 100 into 0.9 into 1. So, 1 is the time required to get a memory get an instruction when there is a cache hit. Okay. So, and 5 is the time required when there is a cache miss. So, the total time that will be required for 100 instructions is given by 100 into 0.9 into 1 plus 0.1 into 5. So, 1 minus 0.9 is the miss rate for the cache, and this gives 140 nanoseconds. So, 1 corresponds to time taken for read when there is a cache hit, 5 corresponds to time taken for read when there is a cache miss, and 0.9 is the cache hit rate. So, 1 minus 0.9, which is 0.1, is the cache miss rate. Now, similarly, time taken for 60 memory operand read operations also becomes 60 memory operand reads. 0.9 is the hit rate, cache hit rate. 1 is the read time, 1 nanosecond. 0.1 is the miss rate, and 5 is the miss time. So, total of 84 nanoseconds for 60 memory operand read operations. So, 100 instruction fetch operations. So, instruction read operations take 140 nanoseconds, 60 memory operand read operations take 84 nanoseconds. Time taken for the 40 memory operand write operations will be a bit different. So, it will be 40, 0.9 is the hit rate in cache, 2 is what 2 nanoseconds is the time taken for a write operation when there is a hit. So, 2 nanoseconds is the time taken for a write operation when there is a hit in cache. So, 40 into 0.9 into 2 nanoseconds plus 40 into 0.1 into 10 nanoseconds. 10 nanoseconds is the time taken when there is a miss in cache. So, therefore, the total time taken for 40 memory operand write operations become 112 nanoseconds. 2 nanoseconds to corresponds to time taken for write when there is a cache hit, 10 corresponds to time taken to write when there is a cache miss. So, total memory access time taken for the 100 plus 60 plus 40. So, 200 total memory operations. So, what is the total memory access time for these 200 memory operations? 140 plus 84 plus 112 nanoseconds equals to 336 nanoseconds. So, average memory access time in executing the sequence of instructions is 336 nanoseconds divided by 200 equals to 1.68 nanoseconds. So, this is the average memory access time, this is the total memory access time over 200 instructions. So, the average memory access time becomes 336 divided by 200, and this is 1.68 nanoseconds for each memory access time on average. With this, we come to the end of this lecture.